Okay, so I'm going to explain how to do Lewis dot diagrams. One thing with Lewis dot diagrams, we only have to do those for covalent compounds because covalent compounds are sharing their electrons. So for covalent compounds, we really want to keep track of exactly how they're sharing their electrons. So let's walk through a quick example. Let's take H2O, which we know as water. So hydrogen is a nonmetal, even though it is on the metal side. Oxygen is definitely a nonmetal. The first thing we want to do is actually count up the number of valence electrons. Hydrogen is in the first column, so that tells us it only has one valence electron. But we actually have two hydrogens. Okay? Oxygen is in that sixth column over near the noble gases. It actually has 6 valence electrons. So one thing that we know is that the column number actually tells us the number of valence electrons. Hydrogen has 1, there's 2 hydrogens. Oxygen has 6 valence electrons because it's in the 6th column. So what we're going to do, we know that these two elements are combining to form a compound. We're going to add up only the valence electrons. So there are 8 valence electrons that we need to use. Now the trick with Lewis dot diagrams, we have to use all 8 valence electrons. One thing with chemistry is we always want to write things as symmetrically as possible. So oxygen would go in the middle, hydrogens would go on either side to start with. We are going to then draw a single bond. Now I'm going to draw it as a line, but your teacher may actually do dots instead of a line, which is perfectly fine. Okay? So that line just represents 2 dots. Now the reason why we draw a line here, or a bond, is because if these elements are in a compound, we can assume that they have at least one single bond connecting them. Okay? One line represents 2 dots, so we've used up 2 electrons here and another 2, so total we've used up 4 electrons just to draw those single bonds. We have 8 electrons to work with, we've already used up 4, so we only have 4 left. One thing for hydrogen, hydrogen is fine with only having 2 valence electrons. So these hydrogens are already satisfied. They already have the 2 electrons that they want by sharing them with oxygen. So those 4 valence electrons we have left, we're going to actually just put them here on the oxygen. So one thing to keep in mind with Lewis dot diagrams is we have something called the octet rule. The octet rule, oct meaning the prefix for 8, every element wants to combine, every nonmetal element wants to combine to try to get 8 valence electrons. Hydrogen is actually one of the exceptions. It's fine with only having 2 valence electrons. Oxygen, on the other hand, just like most other elements, want to have 8. So there's 2 exceptions you do want to keep in mind when we do Lewis dot diagrams. We've already talked about one, which is hydrogen. Hydrogen is fine with 2 electrons. The other exception is boron. Boron is fine with only having 6 electrons. So hydrogen is considered full by having 2 electrons. Boron is considered full by having 6. But every other element on the periodic table wants to have 8. Okay? So the last thing we want to do is we want to look to make sure everybody in our compound has the electrons that they want. If we look at this hydrogen, it actually has 2 valence electrons. It's sharing both of them with oxygen, so hydrogen is fine. We look at this hydrogen. That hydrogen also has 2 valence electrons, so that one's also fine as well. Now if we look at the oxygen, oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen also is fine. It has 4 to itself, and then it has 2 on each side that it's sharing. So it has 8 total. So the oxygen is actually perfect. So this would be the Lewis dot diagram for water. So let's try a few more examples just to make sure that it's a little clearer. Let me try to erase this. Give me 1 second. And as we do the next one, I'll try to draw or write out the steps as we do each of them. And these are the same steps that you can use when you're doing different ones to prepare for the quiz you guys have. So let's say that we have NH3, which we call ammonia. So the first step we want to do is we want to tally up or add up the total. I'm going to put V dot E, that's valence electrons. So we want to tally up the total valence electrons for all the elements in that compound. So we said valence electrons is based off of the column. Nitrogen is in the 5th column, so it has 5 valence electrons. Hydrogen's over there on the far left of the periodic table. It only has 1 valence electron, it's in that 1st column, but there are 3 hydrogens here. So total, we actually have 8 valence electrons that we have to work with. So again, VE is valence electrons. Okay? We know chemistry is all about being symmetrical, so we're going to write this compound as symmetrically as possible. We have 1 nitrogen and 3 hydrogens. Generally, whatever element is first, that's going to be the one that goes in the middle. And then we just write the other ones as symmetrically as possible around it. Now for this last one here, it doesn't matter if you put the hydrogen here or if you actually put the hydrogen up here. So first step, we want to tally up everything. Second step I'm going to write, I'm just going to put symmetry. So just remind yourself, you want to then put the elements as symmetrically as possible. The third step we have here, once we've done that, is we want to draw in single bonds. Okay. So we're going to draw in a line to connect all of these. And we can always assume that if they give us this as a compound, that all of these elements are connected by at least a single bond. Okay? We know a line represents 2 dots, so that's 2, 4, 6 electrons we've used. We had 8 that we can use, and we have to use all 8, and we cannot use more than 8. So we've used up 6 already. We had 8 total. We only have 2 electrons left. One thing we know with hydrogens, they're already fine with 2. So just by drawing these lines connecting them to nitrogen, they're already fine. But I'm going to write an extra step here in case you don't have hydrogen. If you don't have hydrogen, you're going to then want to put all remaining electrons on the outer elements. Okay? So what that means then is, once we draw those single bonds, if there are electrons left over, and we know how many electrons we have to work with because that's step number 1, if we have electrons left over, we're going to put those on the outside ones, so not the one in the middle. In our case, the ones on the outside are hydrogen, so we don't need to put any additional electrons on them. They're already fine. So those 2 electrons we have left over, remember we said 2, 4, 6, we had 6 we used up. Those 2 extra electrons that we have left over, we're just going to dump them right here on the nitrogen. Okay? And step number 5 is probably the most important step. I'm going to say check for 8. And what that means is we said that everyone has that octet rule. Everybody wants to have 8 electrons. So once we put all the electrons on the outer element, if we need to, we always want to go back and double check to make sure everybody has the 8 that they need. Remember, we said hydrogen is fine with just 2, but boron is also fine with just 6. Everybody else wants to have 8. So if we look at these hydrogens, this one has 2, it's sharing them with nitrogen. This one also has 2, it's sharing it with nitrogen. This one also has 2, it's sharing it with nitrogen. So all of these hydrogens are perfectly fine. Let's look at the nitrogen. It has 1, 2, 3 bonds, so it has 2, 4, 6 electrons that it's sharing, and then it has the last 2 to itself, so it actually has 8 electrons, so nitrogen's also fine too. So this would be the Lewis dot diagram for ammonia. We're just going to do 2 more. Let's try one with a charge, and then we'll try one that has more than single bonds, so maybe a double or a triple bond. Alright, so let's try this guy. Let's try SO3. So first thing we want to do, we want to tally up those valence electrons. So sulfur is in the 6th column, it has 6. Oxygen's also in the 6th column with sulfur, it has 6. But we have 3 oxygens. So total we have 6 plus 18, we have 24 valence electrons that we have to work with to try to do the Lewis dot diagram. So the first thing we'll do, we'll put the sulfur in the middle, put the oxygens on either side. Okay, we're going to draw in those single bonds. So that takes up 2, 4, 6 electrons. We have 24 total. We've used up 6, so we have 18 left. Okay? Now we said that once we draw in those single bonds, we're then going to put the remaining electrons on the outer elements. In this case, we don't have hydrogen, so we actually do want to fill up all of these outer elements first. So if we look at this, each of these oxygens already has 2 electrons, so we're going to give each of them the 6 more that they need so that they'll have 8. So I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've actually used up all 18 that we had left. So we have no more electrons left. Okay, so we're going to go to step 5. Check for 8. So we want to check to make sure everybody wants to have 8. Remember, hydrogen's fine with just 2, and boron, if you have it, is fine with just 6. Everybody else wants 8. So we're going to check to make sure all of these guys have 8. So if we look at this oxygen, it has 2, 4, 6, 7, 8. So it has 6 to itself, and it has 2 that it's sharing. Same is true for all these other oxygens. 6 to themselves and 2 that it's sharing. So they all have 8. So the oxygens are fine. Sulfur. How many does sulfur actually have? Well, sulfur has 2 here, and another 2 here. So it's sharing 6 electrons with the oxygens, but sulfur wants to have 8. So sulfur has a problem. So one of the things that we need to do is we don't have any more electrons, so we can't start inventing dots, but we can rearrange the dots that we do have. So what we're actually going to do, we're going to grab these electrons and we're going to share them with the sulfur. So actually what we'll end up with, and I'll write it up here at the top, so these 2 oxygens stay the same, but this oxygen now only has 4 to itself, but now it's sharing 4 with the sulfur. So now sulfur actually has 8 electrons. Okay? And you might wonder, well, why did I take these electrons? How come I didn't take those, or how come I didn't take some from here? It actually does not matter because all of these oxygens are identical. So this is one example of how you could write it. Another example would be, and I'll squeeze it down here. We could have done it there, so we could have taken the electrons from this oxygen. Or, as a third option, we could have actually taken the electrons here from the one at the bottom. So we have 3 different potential Lewis dot diagrams. We have one here, we have one here, and we have one here. So this is a perfect example of something called resonance. So if you have heard your teacher say resonance, that's what this is. Resonance, and I'll write the word up here, we call these resonance structures. So resonance structures is just when you have a compound, so we have SO3, that actually could have 3 different Lewis dot structures. So this is resonance structure. These are 3 different resonance structures. Now on a quiz or test, it's fine if you only list one of these, because technically these are all identical. But your teacher would probably want you to notice that that double bond could be at any one of these spots. So your teacher would probably want you to definitely write all 3 of them. We don't always have resonance. We only have it really happen if we have a double bond that could happen with any of these outer elements. Since all these outer elements are identical, any of these oxygens could make that double bond. So this is an example of something with resonance. All right. Let's try 2 more examples. So I'll keep our list up. See if I can erase this. Okay, so let's try some where we have charges. So you may be given compounds that actually have charges. So let's say you're given a compound like, let's say CN -1. Okay, so we're still going to be able to run through all of our steps. We still want to be able to add up the total valence electrons first. So carbon's in the 4th column. Carbon has 4 valence electrons. Nitrogen has 5. Now we have to address what this charge means. The -1, that means that we've actually gained an additional electron. So we have 1 more electron, almost like a bonus electron that we get. Okay? If this were a plus, so let's say as an example, if you had NH4 plus 1, so let's say you had NH4 plus 1, we would still add up like we normally would. So nitrogen's in the 5th column would have 5 valence electrons. Hydrogen would have 1, but there's 4 hydrogens. The plus 1 now means that we actually have to take an electron away. So we'd actually subtract an electron from the total that we have. So positive charges, you're going to subtract the number of electrons. So if this were a +2, you would subtract 2. If you have a minus, you're going to add that number of electrons. So if this was a -3, you would add 3. But in our case, we have a -1, so we're going to just add 1. The next thing that we would do, we would add all 3 of these numbers together. So 4 + 5 + 1, that is 10. So we have 10 valence electrons that we need to use to combine these two together. So C and N, okay? The first thing we're going to do then, we're going to draw in our single bond. So that takes up 2 electrons. We have 10 to work with. So we have 8 left. Okay, we're going to go to our next step. We're going to put all the remaining electrons on the outer element. Now in this case, it's hard to say which one is in the middle because there's only 2. So you can pick. So let's say we take all these last electrons and we'll fill each of them up. So nitrogen already has 2, so we'll do 1, 2, 3, 4, 5, 6, 7, 8. Now nitrogen has 8. Okay, so now we have 2 left. We'll put those last 2 on the carbon. Okay, and it doesn't matter if you put 6 around the carbon and then 2 on the nitrogen. It doesn't matter because that last step that we'll do, which is check. We always want to check for 8. We'll go back and check, and that'll kind of tell us how we need to rearrange these guys. So we've used up all of our electrons. Now if we go back and check, this nitrogen actually has 8, 6 to itself and 2 that it's sharing. This carbon has 2 to itself and 2 that it's sharing. So right now this nitrogen has 8, but this carbon only has 4. So there's a problem. Carbon wants to have 8. So we're going to need to rearrange some things. Okay? So we're going to actually have to take these electrons from nitrogen and share them. Now the reason we don't take them from carbon is because if carbon were to take these electrons and share them, it's not giving carbon any more electrons. It's just making carbon share its electrons. Okay, so we're going to take those electrons from nitrogen and make a double bond. And then we'll just check to see if that's all we need to do. Okay, so if we check, now this nitrogen still has 8. It has 4 that it's sharing now and 4 to itself. Now this carbon actually has 6. It has 4 that it's sharing and 2 to itself. Remember, one line represents 2 dots. Well, that's still not enough. Carbon only has 6. So we're going to do it again. We're going to take another pair of electrons and dump them in between. So we'll actually end up with a triple bond in order for both of them to have 8. Now carbon has 8. It has 6 that it's sharing and 2 to itself. And nitrogen has 6 that it's sharing and 2 to itself. The only last thing we want to do, and this is something that we have to do when we have things with charges, is we put brackets around the final dot diagram and we put the charge. Okay? That's just to tell someone that looking at this dot diagram, this has a charge of -1, meaning we did this dot diagram with 1 extra electron. And that's what we do just to make sure someone knows. So if we go back up to our example here, when we do if you were to do the dot diagram for this with a +1, you would just make sure after you finished it that you put brackets around it and put a +1 there. So someone knowing looking at this that you did that with having 1 less electron than normal. Okay. So I'll give you one example to try. We'll pause for a brief second and see if you guys can actually get the correct Lewis dot diagram based off of kind of what we've gone over. And then in the next video, I'll explain how we actually do the shapes, how you predict the shapes. So we want to figure out what the Lewis dot diagram for CO3 - 2 would be. So this would be a good time if you want to pause the video, try it, come back and see if you get the same answer that I do. Okay, so hopefully you've tried to do this, and we're going to go through our steps. Hopefully when we finish, you ended up with the same Lewis dot diagram that I'm going to come up with. So in our case, we're going to find the valence electrons first. Carbon's in that 4th column. We have 4 valence electrons for carbon. Oxygen's in the 6th. We have 6 valence electrons for oxygen times 3. Okay, we're going to add those 2 together. But before we do that, we know this minus means we've actually gained some additional electrons. So we have almost like 2 additional bonus electrons that we can add on. So we have 4 plus 18, that's 22, plus 2 more. So we actually have 24 valence electrons to work with. Okay, again, we said chemistry is all about symmetry. So we're going to put the carbon in the middle. We're going to put oxygens on either side. Then we are going to draw in those single bonds, because we can assume that there is at least a single bond connecting all of them. Now that takes up 2, 4, 6 electrons. We had 24, so 24 minus 6, that's 18. So we have 18 left. Now we know in the last step, or second to last step, we're going to take them, once we draw in those single bonds, we're going to take those electrons and fill up all the outside ones first. So if each of these oxygens already has 2, they need 6 more each. So those additional 18 electrons, we're just going to put them all on the oxygens. All right, now we've used up all of our electrons. We have none left. We just want to go back and check to see if everybody has the 8 that they want. And again, remember, hydrogen is fine with 2, and boron, if you ever get it, is fine with just 6. Everybody else wants to have 8 electrons around them. So if we go and check the oxygens, this oxygen has 6 to itself, 2 that it's sharing, so it has 8. This oxygen has 6 to itself, 2 that it's sharing also has 8. And this oxygen has 6 to itself and 2 that it's sharing, which also has 8. So all the oxygens are fine, but carbon has an issue. Carbon only has 6, has 2, 4, 6. So we're going to have to do a double bond. Okay? I'm just going to grab these here. So we're going to make a double bond. So we actually end up with, and then I'm not going to draw them, but these would have the dots around them. Now if you notice, this is one of those resonance structures, because you could have taken the electrons from here, or you could have taken the electrons from any of these other oxygens as well. So the complete answer, to make sure you get full credit, just in case teachers like to take off points, once you notice that there are multiple options, you should try to write all of the possible options there are, just to be safe. So the 3 actual Lewis dot diagrams for this CO3 with the -2 would be C this way, the double bond over here, move this out of the way, okay. And the double bond at the bottom. Just be careful, when we have this double bond, this oxygen now only needs 4 around it. It doesn't need to have 6 dots around it, only 4. So those would technically be the 3 Lewis dot diagrams. And remember, anything that has a charge, we actually have to put brackets around all of these. Just so that someone looking at this knows that we did these diagrams with extra electrons. Okay? So hopefully this was helpful. If you find that you still have questions after going through them, feel free to either text message me or email me. I'll try to make sure to check my email regularly because I know you guys have a quiz tomorrow. But my telephone number is 240-838-4223, or you can email me at csi3943@gmail. And I will I'll be tutoring most of the day today, but I'll do my best to try to respond to emails relatively quickly.